All right, let's just dive right into this explainer. Today, we're exploring this seriously fascinating world of statistical learning. This is basically where we take raw, messy data and transform it into incredibly powerful, actionable insights. Whether you're, say, estimating the exact effect of an ad campaign on product sales, or you're trying to categorize super complex genetic markers, statistical learning is absolutely the fundamental toolkit we use to make sense of the world through data.
But, before we get too confident in our mathematical superpowers, we really have to acknowledge this classic quote from baseball legend Yogi Berra. It's tough to make predictions, especially about the future. It just perfectly captures the ultimate challenge we face as data detectives, right? Because modeling the past, that's relatively easy. But accurately predicting the future is notoriously difficult. So our whole goal today is to understand exactly why that is, and the specific strategies we use to actually overcome it.
So here's our roadmap for today. First, welcome to statistical learning. Then we'll compare supervised versus unsupervised learning. Third, we'll look at flexibility versus interpretability. Fourth, we're tackling the famous bias-variance trade-off. And finally, number 5, finding the perfect balance. Let's get to it.
Section 1. Welcome to Statistical Learning, Building the Data Detective Toolkit. So, at its core, statistical learning is really just about finding the relationship between your inputs and an output. We basically want to find a mathematical function that estimates that relationship. But here's the catch, and it's a big one. We have to accept that there will always be two distinct types of error. First up is reducible error. This is the actual inaccuracy of our model itself, which is great because we can improve it by simply choosing better statistical techniques. But then there's irreducible error. This is the random noise we simply cannot predict no matter what. Think of a patient's daily mood or some variable we just didn't measure. So our entire mission here, it's to minimize that reducible error.
Take a look at this. Notice that cluster of red dots? Those represent observed data points, specifically looking at an individual's years of education versus their income. Our main objective here is to draw a mathematical line or curve right through these points to accurately estimate an outcome. Now, the curve you're seeing, it obviously isn't perfectly hitting every single dot, right? But it doesn't need to. It captures the true underlying relationship, which then lets us predict someone's income based on their education.
Moving right along to Section 2, Supervised versus Unsupervised Learning, Identifying the Problem Type. Okay, before we even think about building a model, we absolutely must determine what kind of learning environment we're actually operating in. This is the core difference between supervised and unsupervised learning. In supervised learning, you have a very clear target you're trying to predict. For instance, if you have historical data on TV, radio, and newspaper ad budgets, and you already know the resulting sales figures, you can train a model to predict future sales. The historical sales data literally supervises the learning process. Unsupervised learning, on the other hand, well, it's kind of like flying blind. You have input data, let's say the browsing histories of online shoppers, or maybe gene expressions in cancer patients. But you have no specific response variable to predict at all. You're just purely looking for hidden patterns. And this is a great visual for that. Notice how the algorithm here has looked at a random scatter of data points and entirely on its own discovered distinct subgroups, or clusters. You can see them separated by the different colors. It wasn't told what to look for beforehand. It simply found the inherent structure hidden within the data, which, as you can imagine, is incredibly useful for things like market segmentation.
Which brings us to Section 3, Flexibility versus Interpretability, the Model Complexity Dilemma.
Now, since computers today are just incredibly powerful, you might logically be wondering, why don't we just use the most highly flexible, insanely complex model for every single problem? Like, why would we ever intentionally choose to use a restrictive simple model like standard linear regression?
Well, when we go all in on flexibility, we get something like this bumpy, highly contoured 3D surface trying to estimate income. It vigorously twists and bends to get as close to the training data points as mathematically possible. But here's the problem. As the model becomes this flexible, it essentially turns into a total black box. It becomes almost impossible to isolate and explain to a client how one single input, say exactly one more year of seniority, actually affects the response. You totally lose the ability to easily explain the why behind the prediction.
So, the golden rule of thumb is basically this. If you need inference, meaning you really need to understand the underlying relationship between your variables, like exactly how a specific drug dosage impacts blood pressure, you absolutely must sacrifice flexibility and stick to a restrictive interpretable model.
But if you only care about pure prediction accuracy, like say forecasting tomorrow's stock price, where you just want the right number and honestly don't care how the algorithm got there, then sure, you can embrace the complex black box.
All right, Section 4, the bias-variance trade-off, the ultimate balancing act.
But beware, even if you only care about pure prediction, you can't just maximize flexibility blindly. Too much flexibility leads us right into the most famous mathematical balancing act in all of data science, the bias-variance trade-off. To really grasp this, especially if you're a beginner, we have to separate how well our model memorizes the past from how well it actually predicts the future. The training error is how well your model performs on the data it already saw during training. The test error is how well it performs on brand new, completely unseen data. Think about it. If you're predicting stock prices, you really don't care if your model perfectly predicts last week's prices, right? You only care if it accurately predicts tomorrow's prices.
Check this out. Here, the gold line is a simple, restrictive linear model. Meanwhile, that squiggly green curve, it is aggressively twisting and turning to hit almost every single training data point. It has a very, very low training error. But guys, this is a trap. It's called overfitting. It is literally learning the random noise, that irreducible error of this specific dataset we talked about earlier, instead of the true underlying pattern. If we actually feed that green curve new data, its predictions are going to be wildly inaccurate. And this classic U-shaped chart perfectly maps out the trap of overfitting. That gray line going down, that's the training error. As flexibility increases, it just keeps dropping, because the model is basically memorizing the data. But look at the red line. That's the test error on unseen data. As model flexibility increases, the test error initially drops, which is good, but eventually it hits a turning point and curves right back up. It rises again precisely because of that overfitting we just saw. This beautiful U-shaped curve for the test error doesn't just happen by magic. It is totally dictated by two competing properties that we must learn to balance perfectly: variance and bias.
Which leads us to Section 5, finding the perfect balance, minimizing total error. Okay, so what are they? Well, variance is essentially the model's sensitivity to the specific training data. If a model has high variance, it means small changes in the training data will cause massive, erratic shifts in the model's shape, just like that squiggly green line we saw a minute ago. Bias, on the other hand, is the model's blind spot. It's the error introduced by assuming the real world is simple. For example, a straight line has extremely high bias because it stubbornly assumes reality is perfectly linear, which, let's face it almost never is. This table right here clearly summarizes the unbreakable mathematical rule we have to navigate. As you increase a model's flexibility to capture more nuance and lower your bias, your variance will inevitably increase because the model becomes way more sensitive to the specific noise in the data. They literally move in opposite directions, always.
So to break it down, if you have low variance but high bias, your model is underfitting. It consistently gives you an estimate, sure, but it's fundamentally inaccurate because it's just too simple. Conversely, if you have high variance but low bias, your model is overfitting. It fits the current data beautifully, but it behaves completely erratically on new data. As data detectives, you are always hunting for that mathematical sweet spot right in the middle, the very bottom of that U-shaped curve that minimizes both variance and squared bias simultaneously.
And here is the catastrophic result when we forget this rule. These box plots show the test error literally skyrocketing as we blindly feed a model more and more irrelevant variables. You might logically think, hey, adding thousands of features gives the model more information, right? But actually, it vastly increases the variance of the coefficient estimates without reducing the bias at all. The noise completely overwhelms the signal, and your test error explodes, making your predictions entirely useless.
Ultimately, by understanding these foundational trade-offs, knowing when to choose between supervised and unsupervised learning, balancing flexibility with interpretability, and carefully navigating the bias-variance trade-off, you completely shift your approach. You stop just hoping a computer will magically solve your problem with sheer processing power, and you start actually thinking like a true statistical consultant, strategically fitting the right tool to the specific reality of your data.
So I'm going to leave you with this provocative thought to challenge your assumptions. Knowing that perfectly predicting the future is mathematically impossible due to irreducible error, how complex will you allow your next model to become before it stops learning the truth and just starts memorizing the noise? Thank you so much for exploring the depths of statistical learning with me on this explainer. Keep questioning the data, and I'll catch you next time.